We've got a solid cylindrical aluminium pole. It's mounted vertically on a concrete slab, and the base of the pole is fixed, so it doesn't move. The pole is 5 meters long and has a cross-sectional area of 20 centimeters squared, and a horizontal force of 120 newtons is applied to the top of the pole. How far will the top of the pole move horizontally in micrometers? So, sorry. So we've got a cylindrical pole. And it's 5 meters high, and we've applied a force horizontally, and that's 120 newtons, and so that means it's going to, the pole is going to move, so it's going to so it's going to move like that. So it's going to be so when you apply a horizontal force to it, that's what you call a shearing force. Okay, and so you've been given the shear modulus of aluminium, and that's equal to 26 gigapascals. So remember, giga is 10 to the power of 9. So the equation for shear modulus, and so what you want to find out, you want to find out how much this will move, and that value there is delta x. Okay? So the horizontal movement in response is delta x. So delta x is equal to question mark, and we know that the force is equal to 120 newtons. Okay, so the equation for shear modulus is equal to force over area, so it's pretty similar to the Young's modulus we went over earlier, and delta x over LO. Okay, so that's your equation for shear modulus. And this time we want to find out what delta x is. Okay, we're going to rearrange this equation, and because it's a hard one to rearrange, I won't go through it. I'll just give you the final rearrangement, which is delta x is equal to the force multiplied by the original length. So here, the original length is going to be the length of the pole. So this is LO, okay? And that's over the shear modulus multiplied by the cross-sectional area. So if we put in the numbers, that's 120 times the original length, which is 5, times the shear modulus, so 26 gigapascals, so giga is times 10 to the 9. And the cross-sectional area, we were told, is 20 centimeters squared. So we're going to write down 20, and we're going to replace centimeters squared with times 10 to the negative 4. So remember, we have to convert that into meters squared. So 20 times 10 to the negative 4 meters squared. And if you do that in your calculator, that will give you 11.5 times 10 to the negative 6 meters. So whatever value you get in your calculator, that will be in meters, so that'll have a whole heap of zeros in front of it. And to turn that into micrometers, you're going to divide it by the prefix for micro, which is times 10 to the negative 6. So if you divide that by 10 to the negative 6, you'll get your answer in micrometers, which is what you want. So that's going to be 11.5 micrometers. Okay? Number 2, ethanol has a bulk modulus of 9 times 10 to the power of 8 pascals. And what pressure change would be required to reduce the radius of a spherical droplet of ethanol by 1%? And that's in megapascals. So, an easy rule to remember about the bulk modulus. So, the bulk modulus, which is given the symbol B, is the amount of pressure that would be required to reduce the volume by 100%. So equals amount of pressure required to reduce the volume by 100%. Okay? So in reality, you'd never be able to reduce the volume by 100%, because if you did that, the volume would be 0. Right? So this is, but that's like an easy rule to remember, because that means that if you want to reduce the volume by 5%, then you only need 5% pressure, 5% of the bulk modulus. Okay, so if you want to, let's say you want to reduce volume by 5%, then let's say that the bulk modulus value is B is equal to, let's just say 100, just for this example. So our bulk modulus is equal to 100 pascals. And want to reduce volume by 5%. So we'll just calculate 5% of 100. So 5% is equal to 0.05. Okay, if you want to convert that into a decimal. So that means 0.05 times 100 will be equal to 5 pascals. So that means that you would need a pressure change of 5 pascals, or 5% of the bulk modulus, to reduce the volume by 5%. Okay? So if it was 3%, you need, if you want to reduce the volume by 3%, then you'd have then you just calculate 3% of the pressure. Okay? So once you know that, these questions become a lot easier. But the problem here, and the reason that this one's difficult, is because they're asking what pressure change would be required to reduce the radius of a spherical droplet of ethanol by 1%, and not the volume. Okay? So remember that. So in this question here, they haven't actually given you the equation for the volume of a sphere. And that's why I said you should write down that equation in your cheat sheet. So the volume of a sphere is equal to 4/3 times pi times radius to the 3rd power. So we want to figure out if we reduce the radius of a sphere by 1%, how much would the volume change? So this one's a bit of math. So let's just say that our initial radius, R1, initial radius is equal to 1, to make it easy. And that means that our final radius is 1% less than the initial radius. So that's going to be 1 minus 0.01, which is 0.99, right? Okay, so everyone with me? So we've reduced the radius by 1%, so our final radius is going to be 0.99. So if volume 1, so the initial volume would have been 4/3 times pi multiplied by 1 cubed. Okay, so that would give you that would be 4.1888 meters cubed. Okay, and then the final volume after the radius has been reduced would be 4/3 times pi times 0.99 cubed, which would be equal to so if you just did 0.99 cubed in your calculator, it would become 0.97, right? So that basically means that it's going to be 97% of the original volume. So if you did that, it would become 4.064 meters cubed. Okay, so that's your new volume. So when you reduce the volume, reduce the radius by 1%, this is how much the volume has changed. So you can find out as a percentage how much the volume has reduced. So you're going to go V2 over V1. So that's 4.064 divided by 4.1888. So if you do that, that's going to give you 0.97. So our new volume is 97% of our original volume. So how much has our volume decreased by? Sorry? Yeah, 3%. So we've reduced our volume by 3%. So then, how much percent of the bulk modulus do we need? Sorry? Sorry? Can't hear you. Yeah, so 3%, 0.03 or 3%. So we're just going to calculate 3% of the bulk modulus, which is 9 times 10 to the 8. So that's going to be 27 million pascals or 27 megapascals. Okay? Oh, so we've changed the volume by 3% because we went from the new volume, right? So this is the new volume here, V2. It was 97% of the original volume. So then if the new volume is 97%, that means we must have reduced it by 3%. Yeah. So this 0.03 just means 3% of the bulk modulus, because that's how much you want to change the volume by. So number 3, you're using a pipette to transport a fluid of density 1.5 times 10 to the power 3. The length of the pipette is 0.3 meters, and the height is of the fluid in the pipette is 0.2 meters. So what's the absolute pressure of the air trapped in the top of the pipette? So we have this column of fluid here, and we know that the height of this fluid is, so height is equal to 0.2 meters. And so we know that the bottom here is exposed to the atmospheric pressure. So the pressure at this point here, at this height, will be equal to the atmospheric pressure. Okay? Which is 101 kilopascals. Okay, and at the top, so at the surface, at the top of the water column, the pressure will be equal to the pressure of the gas inside this air bubble here, or this space. Because remember, it's the gas in here that's pressing down, exerting a pressure on the water. So the pressure at this point of the surface of the water will be equal to the pressure in here. Okay, so what we can do is we can calculate the pressure of the surface of the water, because remember that because we know the difference in height, we can calculate the difference in pressure. So the pressure here is question mark. You want to find out what it is, and which one of these is going to be higher. So remember that as you go deeper in the ocean, the pressure becomes greater. So this pressure up here is going to be less than the pressure down here. Okay, so our pressure is going to be less than 101 kilopascals, which doesn't really help us because all of the options are less than 101. So what we're going to do, we're going to calculate the change in pressure. So change in pressure is the density of the liquid multiplied by gravity multiplied by the change in height. So the density is 1.5 times 10 to the power 3 times gravity, which is 10, times our change in height, which is 0.2. So that's going to be 3,000 pascals. Okay, or we can just say it's 3 kilopascals. Okay. So the difference in pressure between the top and the bottom of the water is 3 kilopascals, and the pressure up the top is going to be 3 less than the atmospheric pressure, so that must mean 101 minus 3 is 98. So that must mean the pressure at the top of the water column is 98 kilopascals. Okay? All right. Number 4, we have a small cylinder of copper and which has a mass of 31.5 grams, and it's resting at the bottom of a beaker. The beaker is filled with water, so that the cylinder is completely submerged. Okay, and the beaker has a cross-sectional area of 7 centimeters squared, and the water level is 12 centimeters above the base of the beaker. So 12 centimeters, that's 12 times 10 to the negative 2 meters, or you could just say that's 0.12 meters. So that's 0.12 meters is the height of the water, and the cross-sectional area of the water is 7 centimeters squared. So the cross-sectional area is equal to 7 centimeters squared. So centimeters squared is times 10 to the negative 4. 7 times 10 to the negative 4 meters squared. Okay, so that's our cross-sectional area. So what's the gauge pressure in the water at the bottom of the beaker? So gauge pressure, that's just the difference in pressure. Okay, so that's delta P. That's pretty easy. Our change in difference in pressure is going to be the density of the liquid times the gravity times the change in height. So the density of the water is 1,000 times gravity, which is 10, times the height of the water, which is 0.12. And that's going to be 1,200 pascals, or 1.2 kilopascals.
Did you use the density, the pressure of water,
The density?
Yes.
Yeah.
The pressure.
What do you mean?
You used 0.12.
Oh, so that's the height?
The 1,000.
Sorry?
The 1,000.
1,000?
Yes.
Yeah, so that's the density of water, because what we're trying to find out, the gauge pressure basically means how much, gauge pressure is how much more than the atmospheric pressure the pressure is. So we know that at the surface of the water, it's open to the atmosphere, so the atmospheric pressure, the pressure will be equal to the atmospheric pressure, and then as you go deeper in the water, the pressure is going to increase. So we've just calculated the difference in pressure between this point and this point. So at the bottom of the beaker, the pressure is 1.2 kilopascals greater than the pressure at the top of the water, which is atmospheric pressure. Okay? Yeah, so that was a good question, because I should have explained that at the start. So our next question is carrying on from this previous question. So I'm going to leave this diagram up here. So we're trying to find out how much did the water level rise when the cylinder was originally placed into the beaker. So remember that whenever we place an object into a liquid, it's going to displace that same volume of liquid. So the height of this column, the height of this water must have increased, right? Because the area is going to stay the same, so the height would have increased when you put the cylinder in. So it would have increased like this. So we're trying to find out how much, we're trying to find out what the change in height would have been when you put the cylinder in. Okay? So first of all, you need to calculate the volume of the cylinder. So we've been given the mass and the density of the cylinder, which is copper, right? So volume is equal to the mass divided by the density. So again, we're using this equation for volume, mass, and density. Okay, so that's really important. The mass was 31.5 grams. So we have to convert 31.5 grams into kilograms. So that's going to be, so you're trying to add a prefix, so you're going to divide by that prefix. So 31.5 divided by times 10 to the 3. So that's going to be 0.0315. Divided by the density of copper, which is 9.0 times 10 to the power of 3. So the volume of your copper cylinder is going to be 3.5 times 10 to the negative 6 meters cubed. Okay. So we've got the volume of the cylinder, and so that's the volume of liquid that's been displaced. And so the volume can be calculated by doing length times width times height. So length times width is the area, right? So times the height. So we can say that the change in volume is equal to the area multiplied by the change in height. Okay, because we know that the area can't change. We've got a fixed area because it's just going straight up and down, so the area doesn't change. So any change in volume is due to a change in height. So we'll just rearrange this equation for delta H. So change in height is equal to change in volume divided by the area, cross-sectional area. So that's 3.5 times 10 to the negative 6 divided by 7 times 10 to the negative 4. Okay? And that will give you 0.005 meters. And if you want to turn that into centimeters, you're just going to divide that by 10 to the negative 2. And that's going to be 0.5 centimeters. Does everyone get this part? Does anyone not understand?
Wait.
Okay, sweet. So sorry, this is a three-part question. So, what's the magnitude of the buoyant force exerted by the water on the copper cylinder? So, we want the buoyant force, so the equation for that is the density of the liquid multiplied by the volume that's being displaced multiplied by gravity. And the density of the liquid we know is 1000. And the volume is going to be equal to the volume of the cylinder, which we just calculated. So that was 3.5 times 10 to the negative 6 times gravity, which is 10. So that's just going to be 3.5 times 10 to the negative 2 newtons. Okay. So that's just using the volume that we calculated earlier in our last question. And our next one is the one that we did in our previous tutorial. So I put that in there by accident. So we'll go over the page to number 8. So we have an upright, uniform cylindrical tank containing an unknown fluid, is weighed and measured. So the base of the tank has a cross-sectional area of 3.2 meters squared, and the mass of the fluid in the tank is 2.4 times 10 to the 4 kilograms. The tank's open to the atmosphere at the top. So what's the gauge pressure at the bottom of the tank when it contains the fluid? So we've got we've got our cylindrical tank. And it's got some fluid inside it. And we know that so the cross-sectional area is equal to 3.2 meters squared. So that's already in meters squared, so we don't have to convert that one. And the mass of the fluid is equal to 2.4 times 10 to the power 4. Okay, so we want to know the gauge pressure. So the gauge pressure is how much more than the atmospheric pressure the pressure is. So at this point here, at the surface of the water, the pressure is atmospheric pressure, right, because it's open to the atmosphere. And we want to know the pressure at the bottom of this tank, which is going to be P gauge equals question mark. Okay? So we just want to know how much more the pressure will be at the bottom of the tank compared to the top. So that means we just need to calculate the difference in pressure, or delta P, which is going to be rho G delta H. Okay? So here, it's a bit hard because we don't actually have the height of the tank. We only have the cross-sectional area. So if you remember, we actually had another equation for delta P, and that equation was delta P is equal to delta F over A. Okay? So that's the other equation that we had for delta P. And so the amount of force that's being applied is going to be the weight force of the water. So that's mass times gravity, right? So we can just say the the force is going to be mass times gravity over the area, and we know the area, so we can calculate delta P. So mass is 2.4 times 10 to the 4 times 10 over our area, which is 3.2. And that's going to give you 75,000 pascals, which is 75 kilopascals. Okay? Right. So it's just like looking at your cheat sheet and looking at what other equations do I have and what are the variables or the values that I know, and can I calculate something else to make it fit. Okay, so it's just like experience. Like the more you do it, the better you'll get at it, and that's why I say like it's good to do all these passing grade questions, because it's always going to be quite similar. So we have a last one, and this one's quite hard. So I'll try and take it slow, but yeah, don't be too worried if you don't really get it. So we have a cubical box, and it has each of its sides, so width, height, and length is 20 centimeters. And the box is initially upright and empty, and the lower third of the box is submerged. Okay, so it's 33% is submerged. And remember that rule that I told you about? So if 33% of it is underwater or submerged, that means that the density must be 33% of the liquid that it's in. And so a cat is placed in the box, and the box sinks a further 3 centimeters into the water while remaining upright. So we want to find the mass of the cat. And you've been told that the density of water is 1,000 kilograms per meters cubed. So first of all, you need to calculate the mass of the box. So our first step, we're going to calculate the mass of the box, and the mass of the box will be equal to the density of the box multiplied by the volume of the box. So the density of the box, so we said that because 33% is underwater, or 1/3 is underwater, it means that the density must be equal to 1/3 of the density of water. Right, so the density of the box is equal to 1/3 times the density of water, which is 1,000, which means the density is 333.33 kilograms per meters cubed. Okay? Does everyone understand that part? Cool. So that's really important to understand. That's like going to come up a lot, and so just remember that. So 333.33 times the volume of the box. So that's just 20 centimeters cubed. 20 centimeters is 0.2 meters, so we have to have it in meters, remember? So 0.2 cubed, okay? So if I just write it out here, volume of the box is equal to 0.2 cubed, because it's 0.2 times 0.2 times 0.2, which is going to be 0.008 meters cubed. Okay? So the mass of the box is going to be 2.7 kilograms. So we've got that. So that's the first part of our problem. That was the easy part. I'll get rid of this because I need the space. So I'll get rid of those two. So the mass of the box is equal to 2.7 kilograms. The volume of the box is equal to, what did you say? 0.008 meter cubed. Okay, so we've got those two values now. And so after the cat is put in, we know that more of the box has been submerged, so the density of the box has increased, right? So the volume that is now submerged is equal to, so we have the box here. Okay, so now, so this was um, 0.2, 0.2. Okay. So the volume of the box that's now submerged is going to be 0.2 divided by 3, right? So I'll just start again. So we'll just do the length and the width first. So the volume is going to be length times width times height. So that's 0.2 times 0.2. So that's the length and the width. Okay, so now the height is the tricky part. So the height is going to be 0.2 divided by 3, because remember only a third of the height was underwater. So 0.2 divided by 3, that was the original height that was underwater, but it sunk an additional 3 centimeters. So we're going to add 0.03 meters. Okay? So that's the height that's now underwater. Okay? And if you do that, the volume that's now underwater is going to be 3.867 times 10 to the negative 3 meters cubed. And you're going to find out the percentage of the box that's now submerged. So that's going to be the volume of the box that's submerged divided by the volume of the total volume of the box. In our next question, we have a cubical box with dimensions of 20 centimeters on each side. So the total volume will be 20 centimeters cubed. And it's floating, so we know that the density of that box is less than the density of water. And we know that the density of water is 1,000 kilograms per meters cubed. So we want to find out the mass of the cat that's put into the box. And before the cat is put in, only 1/3 of the box is submerged, whereas after the cat is placed in the box sinks another 3 centimeters into the water. So what we need to find out here is the difference in volume. So what's happened to the box is that the volume of the box that is submerged has increased. So we want to find out the change in the volume that has been submerged. So our initial volume. So this is the initial volume that's submerged. So that's going to be equal to our dimensions. So this will be 0.2 times 0.2. So remember that's 20 centimeters equal to 0.2 meters. And so let's say that if we had a cube here, okay, so 0.2, 0.2, and 0.2. So this will be our length. Let's say this is our length, this is our width, and this will be our height. Okay, and we know that initially only 1/3 of it was submerged, but then after the cat was put in the box, another 3 centimeters was submerged. So this is the volume that was submerged initially, and that's what we're looking for. So because we know that 1/3 was submerged, so now this is length and width, and now the height will be 0.2 divided by 3. So 0.2 divided by 3. Okay. And so that will give you an answer of 0.00266666. But we can also write that as, because it's 0.00, so there's 3 zeros. So we'll write that as 2.6667. So we want to keep as many significant figures as you can. I think if we have 5 significant figures, that's usually enough, just so we don't get rounding errors. So times 10 to the negative 3. Remember there's 3 zeros. Okay, meters cubed. So that's our initial volume that's submerged. And then now we have to find out the volume of the box that's submerged after the cat's been put in. So volume submerged final will be equal to, again, the length and the width that's submerged is going to stay the same. So 0.2 times 0.2 times, but now this time it's 0.2 divided by 3 plus 3 centimeters, which is 0.03 meters. Okay, so that will give you 0.0038666666, and we'll write that as 3.8667. Round that to the, because it's 6, it'll round up, times 10 to the negative 3, because it's less than 1 and we've got 3 zeros, meters cubed. Okay, so now we've got our initial volume and our final volume, so we can calculate our change in volume. So our delta V will be equal to VF minus VI, final minus initial. So that's going to be 3.8667 times 10 to the negative 3 minus our initial volume, which was 2.6667 times 10 to the negative 3 meters cubed. Okay, so that will give us 1.2 times 10 to the negative 3 meters cubed, or in other words, that's 0.0012. Okay. So now we figured out our change in volume. So our change in volume will be proportional to our change in mass. So the change in mass of the box will be equal to the mass of the cat, because the cat's being put in the box. So now we can say that our change in mass is equal to our change in volume multiplied by the density, and because the volume that was submerged will be the same volume as the volume of water that's being displaced, so this will be the density of water, because it was the water that was being displaced by the extra volume that was being submerged. So our change in volume is 1.2 times 10 to the negative 3, and the density of water is 1000, so that's going to give you 1.2 kg. Okay, so the mass of the cat is going to be 1.2 kg, and that's going to be option A. Thank you very much.